Okay, calculus, video 2, the limit definition of a derivative. All right, so this is when we start diving into finding out what a derivative is, and we're starting with the most basic definition, the limit definition of a derivative. It, it revolves around the secant line, tangent line difference that we were talking about back in video 1. So just as a reference, a secant line is a line that intersects 2 points on a curve, right? So let me just kind of have a point in red there. If I pick a second point in red, maybe right here, the line that connects those two, close enough, the line that connects those 2 points is called a secant line, right? Secant line. It turns out that the slope of the secant line, the change of y over change of x, so we're talking about the change of y, the vertical distance from the left point to the right point, change of y, divided by the horizontal distance, the change of x, the change of y divided by the change of x, that is the slope of the secant line. And I was saying down here, the slope of the secant line, delta y, or change in y over delta x, is the average rate of change for the function. So it's what is that function changing? How much is that function changing over that particular either x, delta x, or time change, if we consider x to be a change in time. That is the slope of the secant line. Remember, slope is delta y over delta x. Okay, good. What we were looking for here, if you remember back in video 1, is we said the derivative, the idea of a derivative is the slope of the tangent line. Now, a tangent line is a line that intersects 1 point on a curve in a particular neighborhood. And what I mean by that is, let's pick that red point on the left again. I'm going to just go ahead and make it green this time to change the colors. Well, we tried. The tangent line. Let me try that again. Drawing lines is not my forte. The tangent line looks something like this line in green. It intersects that curve at only 1 point. And I said in a neighborhood down there because technically this looks like maybe a cube function, this f of x cube function here. This is our function f. This tangent line could intersect that curve at a second point somewhere later on down the road. It doesn't matter. We only really are thinking about in this sort of neighborhood that we're looking at right here. As you can see, that secant line, that line in red there, we said it's a line that touches 2 points on a curve. If you look, it actually touches a third point on the curve, kind of up here in this region, but we don't care about that. We're looking at just in a particular neighborhood, it touches 2 points on the curve as opposed to 1 point. All right, the slope of the tangent line, dy dx, and we're using d here as opposed to delta to designate a really small change, is what's called the instantaneous rate of change for the function. It's how much is the function changing at that one particular point. That is the idea of a derivative. And so the question is, how do we get a formula for finding the derivative? Or asked another way, how do we get a formula for finding the slope of that tangent line there in green? The way we do so is we use a series of secant lines that approach the tangent line. So for example, I have this secant line here in red. If I put some variables down here, I've already called this x, this point in that's green on the left-hand side here, the left-hand point, x value, and its y value would then be the function value at x, or f of x. So this point, let me kind of label this here. This is the point x, f of x. And to create the secant line in red, what I'm going to do is pick another point sort of down the road from x, this point in red up there. And the x value there is x, the original x value, which was back over here, plus some amount. And people use the letter h here, or you might see instead of h, sometimes we'll write that as x plus delta x, meaning x plus some change in x. Here I'm just going to use h instead of delta x, just for simplicity's sake. That makes the function value here f of x plus h. So this becomes the point. This is the point x plus h, that's the x value. And that is at the function value f of x plus h. All right, so we have 2 points. We have the point x, f of x on the left. We have the point x plus h, f of x plus h on the right. And the slope of the secant line is simply the change in y over the change in x. Right, it is how much is the x changing, that's the delta x. How much is the y changing, that's the delta y. We'll start with the delta y. We see the delta y is just the second y value, f of x plus h, minus the first y value, f of x. So the delta y, the change in the y value, is f of x plus h minus the f of x value. And the delta x is the right-hand x value, x plus h, minus the left-hand x value of x. Here, though, you see the x's cancel, and we're just left with h. That should make sense. The distance between x and x plus h is a distance of h. So the slope of the secant line delta y over delta x, slope of the secant line, delta y over delta x, is equal to f of x plus h minus f of x divided by h. That's the change in y over the change of x. The problem we have right now is this slope, I'm going to call it m1, the slope of that secant line, is not really close to an approximation for the slope of this green line. Just call it m over here. That's the slope of the tangent line. And if I was guessing, I would say the slope of m1 in red there might be like, I don't know, 2/3. Go up 2 over 3. Whereas the slope of the tangent line might be like, it kind of looks like a 4 over 1, something like that. It's not a very good approximation. And so the question is, how do we get a better approximation? The answer to that is we bring our second point closer to our first point. So for example, we start with x and x plus h. Instead of having our x plus h here, let's move it over here. Let's say x plus h is now here. All we're doing here is picking a smaller value of h. Maybe our first value of h was like 2, so we did like x and x plus 2. And now our h is like 1, right? So we did now x and x plus 1. It doesn't have to be those numbers. I'm just saying we're picking a smaller value of h than we picked the first time. What that's going to do, and I'll use a blue dot here, that's going to create a point right here. Now this point is, again, x plus h, a smaller h than we had before, and f of x plus h. The slope of the secant line is the same formula, but now look at the secant line that we have here, connecting the two dots. Best I can draw. Although it's not still a great estimation, here let's call this M2. This slope M2 of the blue line is not a great estimation of M. It's a lot better than M1 was. And what we did is we just keep doing this. We keep moving x plus h closer to x. In other words, we're taking h and making it smaller and smaller. All right, we may do one more. Let's see if I can make one more without making this too big of a mess here. Let's pick orange, a little bit closer. Now this is our x plus h, or so maybe our h value here is like 0.2 or something, right? It's really close. And now we get a secant line that looks like this, which is an even better approximation of that green line. Let's call the slope of this one M3. All right, M3 is a pretty close approximation for M. So what we're going to do is we're just going to keep bringing it closer and closer and closer, zooming in, into where that h really is very, very, very small. In fact, now is when limits come into play. All right, so we can say the slope of the tangent line this time, right, that m in green, whatever that slope of the tangent line, which I estimated looks like 4 over 1 to me, whatever that is, can be found by using closer and closer approximations of the slope of the secant line. And again, what's happening is the h's are becoming smaller, right? We're not adding much onto the x. We're adding smaller and smaller amounts onto the x. So like I said, to do that, we need a limit. It's the limit as h goes to 0. Now what that means is h, we're not letting it be 0, because then you'd only have 1 point and not 2. We're saying what happens as the h, the distance from x to x plus h, that distance h, is smaller and smaller and smaller. What happens is the slope of the secant line becomes more and more the slope of the tangent line. And so the slope of the tangent line can be given as the limit as h goes to 0 becomes really, really small, of f of x plus h minus f of x over h. And this is called the limit definition of a derivative. And there you have it. That is what we're going to be working with. We have the limit definition of a derivative. It's the limit as h goes to 0 of f of x plus h minus f of x over h. And what I want you to remember is that is just a series of secant lines, looking at the slopes of the secant lines, the change of the y value or the change of the x value, as that h becomes smaller and smaller and smaller. Could put a big star by that one. We're going to need that quite often. All right, let's take a few minutes and maybe do an example of what this might look like. Let's see, so I need a function. Let's do a function f of x equals 2x squared plus 3. That's a nice quadratic. We should have a decent picture of what that looks like. It's the x squared function, right? That is moved up by 3, kind of like that. And let's look at the point here, say 1, 5. All right, if you plug in 1 into that function, 1 squared is 1, times 2 is 2, plus 3 is 5, so we get the point 1, 5. What I'm looking for is, what is the slope of the tangent line at that point? And that's not a good drawing. Let me try that again. I'll take that. What is the slope of this tangent line at the point 1, 5 to the curve 2x squared plus 3? f of x equals 2x squared plus 3. What is that slope? That is the limit definition of a derivative. So here's how we do that. We take the limit as h goes to 0. We're using that formula up here. Scroll back up. We are using this formula right here, the slope of the tangent line, the one we have starred. The limit as h goes to 0 of the change of the y value, f of x plus h minus f of x, over the change in the x value, which is just h. And we're going to use our function here is 2x squared plus 3 to do so. So in order to apply this limit definition of the derivative, I need to know what is f of x plus h, so I can plug that in there. And I need to know what is f of x. Well, I have f of x. F of x is right here. F of x is 2x squared plus 3, so that's going to jump right in there. But what is f of x plus h? Hopefully we remember, kind of side note here, that f of x plus h is the original function f of x, where I plug in x plus h every time I saw an x. Now there just happened to be one x in this particular function, but if there were multiple x's, an x squared term, an x cubed term, we would plug x plus h into all of them. Now remember, to multiply this out, x plus h squared, that's x plus h times itself. Anything squared is times itself. So I'm going to take this 2 and multiply it I'm just going to take that in the outside, leave the 2 in the outside, multiply the x plus h times the x plus h. And don't forget the plus 3 on the end. This would be 2x squared. I have 2 of these xh's, so 2xh plus h squared plus 3. Distribute the 2, so that's 2x squared plus 4xh plus 2h squared. Don't forget to distribute the 2 right to all 3 terms, plus 3. And this is f of x plus h. So that whole thing, right, this whole thing, well, this part of it anyway, gets plugged in right there into the f of x plus h. So it's going to look like this. It's long, and you'll get used to this. We have the limit as h goes to 0 of f of x plus h, which is 2x squared plus 4xh plus 2h squared plus 3, minus, and I like to put this in parentheses here, the f of x function, the entire f of x function, which was our original 2x squared plus 3. Again, I like to put that in parentheses, because I'm subtracting the whole thing. If I don't put it in parentheses, what happens is, a lot of times, you'll see this. You'll see minus 2x plus 3. And that's not right, because you're subtracting the 2x squared, and you're subtracting the 3. So, parentheses helps me to remember to subtract all those terms, all over h. Here's the great thing about this. Once you have this written down, every term inside this parentheses will cancel with something from the first term f of x plus h. So what I see here is I have a 2x squared here in the first part, minus a 2x squared. Well, 2x squared minus 2x squared cancel. Also, in the first f of x plus h, I have a positive 3. I want to write over the plus sign. I have a positive 3 minus 3. So the minus sign here, and 3 minus 3 is 0. That also cancels. That leaves us with the limit. Keep writing the limit each time until we're at the end. The limit as h goes to 0, 4xh plus 2h squared over h. Now, this looks a little better, a little less complex than before after canceling. What I see now, what you should notice is, and this will happen every time, in your numerator, every term has at least an h. I have a 4xh, there's an h in that term. I have a plus 2h squared, there's h squared, or 2 h's multiplied in that term. That means I can factor out an h from the numerator. Again, write the limit as h goes to 0 until we use that. If I factor out an h, whoops, you don't need that last part, 4x, if I factor out an h, I'll have left in parentheses 4x plus 2h, right, factoring h out of those two terms over h, and what we see is the h's cancel. What's happening here is as h is going to 0, this h would go to 0 on top, and the h on bottom would also go to 0, and that creates a 0 over 0, which is indeterminate. By factoring the h out and being able to cancel them, we now have the limit as h goes to 0 of 4x plus 2h. We no longer have the indeterminate 0 over 0 form. We can now let h go to 0. Let h get as close to 0 as we want, which in this case we're 2 times something very, 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 very close to 0 is basically 0. So this h goes to 0 here, and we get the limit. Oh, I'm sorry, I don't need the limit anymore if I'm going to use the h going to 0. We get 4x plus 2 times this h going to 0. 2 times 0 is 0. That is 4x. This is the limit definition of the derivative. In other words, it's the derivative. It's the derivative function of f of x equals 2x squared plus 3. 4x is the derivative function of f of x equals 2x squared plus 3. Now, we don't want to have to write out the derivative function of f of x equals 2x squared plus 3 each time, so we need a notation to represent the derivative. the derivative, we're going to use the notation f prime. It's not a 1 there, that's like a little slash. F prime of x to denote the derivative function of whatever original function we had. So in our case, we have f prime of x is equal to 4x. And you might be asking yourself, well, I thought we were finding the slope of the tangent line. And we are. Here's the great thing about the derivative function. It tells you the slope of the tangent line at any point x on the curve. Our curve here being 2x squared plus 3. At any point on that curve, we can find the slope of the tangent line. And the way we do that is, well, what point do we want? Let's go back up. We wanted the slope of the tangent line to occur at the point 1, 5. This is an x value of 1 and a y value of 5. That is the x value of 1 and a y value of 5. So to find what is the slope of the tangent line at that point 1, 5, we come down here to our derivative function, f prime of x is equal to 4x, and we plug in the value of x at the point that we want the slope. So if I want, what is the slope at 1, 5, I would use an x value of 1, and I'd say f prime of 1, that's 4 times 1, that's 4. What we're saying here is m equals 4 is the slope of the tangent line at the point 1, 5 on the graph of f of x equals 2x squared plus 3. So we found the slope. The slope of that tangent line is 4. That's great. That's really all I asked for. But let me extend it just a little bit further. Not only can we find the slope of that tangent line, which now we know is 4, we can find the equation of the tangent line. It's just a line, right? Equation of a line, y equals mx plus b. Or if you want, y minus y1 is equal to m times x minus x1, right? Those are two equations for lines. Y equals mx plus b, where m is the slope. Or y minus y1 is equal to m times x minus x1. In this case, I want to use the second one here. The y minus y1 is equal to m times x minus x1. We know the slope. The slope is 4. We know the point, 1, 5. That means y1, 5, x1, 1, and we find the equation of the line. So we have y minus 5 is equal to 4 times x minus 1. Again, we're finding the equation of a tangent line. Equation of the tangent line. Y minus 5 is equal to 4 times x minus 1. Distribute the 4. Y minus 5 is equal to 4x minus 4. Then add 5. And we get y equals 4x plus 1. This is now the equation of the tangent line. You can see that the slope there is 4. And if you go back up to our graph in green here, we can see that tangent line in green. Yeah, I believe that is y equals 4x plus 1. Makes sense to me. I think that looks pretty good.